Hello, my name is Gavin Bierman, and I work in the Java platform group at Oracle. And this is my talk on data-oriented programming in Java. So today I'd like to introduce you a new technique of modeling and processing real-world data in Java using some recent features. Project Amber has brought lots of great individual features to Java: local variable type inference, switch expressions, text blocks, records, sealed classes, pattern matching, and so on. These are all great features in isolation, but they've been carefully designed to work even better together. They're more than the sum of their parts. In this talk, I want to show you how they combine to offer you a new style of Java programming, one that we call data-oriented programming. But before we start, I don't want you to get the wrong impression. I'm not suggesting it's the death of object-oriented programming. I'm not saying rewrite all your code in the data-oriented style. The way I see it is that data-oriented programming is a new programming style for certain tasks, and it fits perfectly alongside classical object-oriented programming. You can write it all in Java. Let's start by quickly considering what object-oriented programming is. Object-oriented programming, like all paradigms, aims to manage the complexity of our software systems. This complexity comes in many forms, and not all paradigms handle all forms equally as well. As the name suggests, object-oriented programming encourages us to model complex entities and processes using objects combining state and behavior. This encourages encapsulation, where the behavior mediates access to the state, and polymorphism, where multiple kinds of entities can be interacted with using a common interface. Object-oriented programming has been incredibly successful. It's great. It's particularly great at defining and defending boundaries. We have a lot of boundaries in our software systems. Your application and your libraries are usually not written by the same people. That's a maintenance boundary. They're usually not compiled together. That's a compilation boundary. You can compile against one version of a jar and run against another. That's a versioning boundary, and so on. There are lots of boundaries. Object-oriented languages provide us with tools for precisely defining, navigating, and defending these boundaries. In fact, they're so good at this, we almost forget that these boundaries are there. Dividing a large program into smaller parts with clear boundaries helps us manage complexity because it enables modular reasoning, the ability to reason about one part of the program at a time. But things have changed. Java was invented in the era of the monolithic application. It's a fantastic tool for building those sorts of apps. But things have changed. Many, not all, but many, large applications are architected differently nowadays. Rather than architected as a single monolith, larger applications are composed out of many smaller services. These services are used for many applications. This has a number of consequences. Firstly, as they're smaller, there's less need for internal boundaries. Smaller services can be maintained by a single team, maybe even a single person. And with smaller services, there's less need for modeling long-running stateful processes. Java's approach of class-based modeling and strong typing are still tremendously important for smaller programs, just in different ways. Again, I'm not throwing away object-oriented programming here. Where object-oriented programming has classically encouraged us to use classes to model large business entities and long-lived processes, these smaller code bases with fewer internal boundaries will often get more mileage out of using classes to model data. What do I mean by that? Well, if you look at these services, they consume requests that come from the outside world, such as HTTP requests with untyped XML, JSON, or YAML payloads. But only the most trivial of services would want to work directly with data in this form. We're Java programmers, right? We don't want to represent numbers as strings of digits, but rather as Java ints or longs. We'd like to represent dates as classes like local datetime, and lists as collections rather than some long comma delimited string. So external untyped data should be represented internally as Java data. And of course, we'd like to validate that data at the boundary. So what we need is a nice way of representing this data as Java data. So now we can get to the punchline. Data-oriented programming is a new tool in the Java programmer's toolbox to write these sorts of services. Data-oriented programming encourages us to firstly model external data as immutable Java data, and secondly, to keep the code that embodies the business logic of how we act on that data separate. And that's it. I'm going to go into some detail about how this works in a moment. Now, of course, this is all possible to do right now in Java. Perhaps some of you are writing programs in this style already. But Project Amber is delivering features that are going to make this sort of program dramatically easier to write, reason about, and maintain. In the rest of this talk, I'm going to walk you through these new Project Amber features and give you some examples of this data-oriented programming style for Java. The first feature we need are record classes. Here's an example of a very simple data type that we might need to model, a point, which is a pair of integers. We've all written code like this before. We love how in Java we give this class a name and then our points are type checked in the program. A point has two immutable fields for the integers and a constructor. But look at how much other code we have to write. We have to write accessors as we'd like to make the two integer fields private, as it's good programming practice. We have to write an equals method so we can compare 2 points. We have to write a hashcode method so we can put points inside certain collections. We have to write a toString method so we can print the points out. This is a lot of code, and even if our IDE writes this code for us, a lot of the code is really boilerplate after all. We still have to read it. It's easy over time, if the data type evolves, to forget to update some things, and then we're left with some very tricky bugs to hunt down. The real point I'm making here is whilst object-oriented languages are very flexible, you can model anything in them, for simple data, we currently have to pay a high price. Let's lower the price you have to pay to declare simple data types. Record classes finally give us a way to just say what we want. On the right-hand side is an equivalent declaration of a class, a record class called point. Between the parentheses, we declare there are two integer components, x and y. That's it. The compiler can auto-magically generate all that boilerplate on the left for you. If you have a simple data type, then record classes let you say what you want and only what you want. Moreover, as we'll see, other language features will be able to build upon this. It's a very low price to pay. Just to hammer home this equivalence, here's our declaration of the record class point. But recall, I said that a record class is just a special sort of Java class. So to create instances of a record class, we just use the familiar new expression. Clearly, as a point has two components, I expect the constructor to take two integer arguments. I wouldn't expect there to be a constructor taking fewer or more values. All points have two components. That's what the declaration says. Record classes automatically provide an accessor method for every component. And remember that all components are immutable, so any attempt to mutate them results in a compile time error. Record classes automatically come with those three important methods that I mentioned earlier, so we can use them in our code. First, they come with an equals method that compares values only using the components. They come with a hashcode method that uses only the component values to compute a hash. And lastly, they come with a toString method, so I can print them to the screen, for example. Now, there's a lot more. Record classes are special sorts of classes, so you can define methods as you would expect. You can define your own versions of those three methods. You can even write your own constructors. We give you a special compact syntax to write the canonical constructor and so on. But for the purposes of this talk, this is all you need. The second feature that we need from Project Amber are sealed classes. Now, they may seem different from record classes, but they interact with each other in a very powerful way to enable richer modeling of data. Sealed classes address a long-time limitation in the Java language. Imagine we want to model simple arithmetic expressions. We have an interface expert to model these. We have the design goal that there are three sorts of expressions: constants, adds, or multiplies. So we write three final classes, one for each. But actually, this doesn't model precisely what we want. As we want expert to be widely accessible, we've made it public, but it's also widely extensible. We can stop our own implementations of constant, add, and multiply from being extended by making them final, but we can't stop new implementations of expert, like divide, being declared somewhere else. If an instance of divide were to make its way back to code that expected only the first three implementations of expert, then bad things could happen. So we've added a new modifier to classes and interfaces to restrict who can extend it. A sealed class or interface then has to specify completely the classes or interfaces that extend them in a new permits clause. For example, here we have sealed the interface expert, and we have spelled out in the permits clause that the three subclasses permitted to implement it are constant, add, and multiply. Attempting to declare a subclass not on the list results in an error at compile time. Whilst at runtime, the VM will refuse to load class files for unpermitted subclasses. So sealed classes and interfaces allow us to declare hierarchies that model more precisely what we want. So now if we have to model alternatives or choices between data types, we have a tool directly available to us to do so. And we'll see in later examples this is very useful. Because we expect it to be common to co-declare the base type with its implementations in this manner, when all the subtypes are declared in the same compilation unit, we allow the permits clause to be omitted and infer it to be the set of subtypes declared in the same compilation unit, as given on the slide. Okay, final feature from Project Amber that we'll use extensively in data-oriented programming, and that's pattern matching. We've all written code like this before. We use instanceof to test a value. In this case, the test is whether a value O is a string. Then we'd like to use the string value. But we have to declare a local variable and use an explicit cast, which is a pain, right? We have to say the same thing 3 times. I've highlighted them in the code. This sort of noise makes things harder to read than they ought to be. And any code that's hard to read is typically where the bugs are. A very common cut and paste error, in fact, is where the type of the instanceof and the cast end up out of sync. This results in very hard to find bugs. But even worse is the fact that we know the cast must succeed because of the test in the instanceof expression. Pattern matching fuses into a single operation these 3 things we've highlighted in the code: the declaration and conditional initialization of local variables, testing, and casting. Pattern matching allows us to rewrite the code as follows. The code in the blue box is a pattern. We don't need the local assignment or the cast. We can just use the variable from the pattern. So what's going on? Well, let's break it down. A type pattern looks like a variable declaration. Not by accident, it looks like a variable declaration because it is a variable declaration. We sometimes call a variable that's declared in a pattern variable. What's different is the semantics. A pattern embodies a test. Pattern matching is the process of testing or matching a value against that pattern. In this case, a type pattern is a test about the runtime type of the value. Here the test is whether the value is a string. If the value is not a string, then we say that pattern matching fails. If it is a string, then we say that pattern matching succeeds. And as a consequence, the variable s will be initialized with the result of casting the value to the type string. Where can a pattern appear? As you can see in this example, we've enhanced the instanceof expression. So on the right-hand side, you can write not just a type, but also a type pattern. Now, there are some other places where a pattern can appear. We'll see them in a moment. The semantics of a pattern instanceof is pretty obvious. If the pattern matching succeeds, then the instanceof expression evaluates to true, and if the pattern matching fails, then the instanceof expression evaluates to false. And as a result, You can use the pattern variable s in the body of the then block, as we see in the code at the top of the slide. And as you can see, there are no casts in our code. The casts have been rolled into the semantics of pattern matching. So it's handled by the compiler, which means that there's less chance for us to get it wrong. The compiler never makes a mistake. This is using patterns in instanceof expressions, but we let you use them in other places too, in particular in switch expressions and switch statements. The basic idea is simple. In today's switch, the switch labels in a switch block must be constants. We'd like to permit them to be patterns. Here's an example at the bottom of the slide. We're switching over the value O of type objects. And inside the switch block, we have a case for when the value of O matches the string S pattern. If it does match that pattern, then this clause will apply and we will execute the statement on the right of the arrow. But of course, the whole point of a switch is that we have a number of clauses in the switch block. So we can write code such as this. Here we have a case for when the object is an integer. We have one for when it's a string, and also a default clause as well. Now, the eagle-eyed amongst you will have figured out that a switch like this that uses all type patterns is essentially a type switch, which was actually a highly requested feature, except that with pattern matching, it's actually better because you get to use those pattern variables in the body on the right-hand side of the arrow. The compiler figures out all the scoping and the typing for you, no worries. Here's a beautiful example of Project Amber features combining to offer something really nice. Remember that sealed hierarchy for mathematical expressions? Let's imagine that we have a value, E, of type expr. Let's switch over it. Well, as it's a sealed interface, we know that it must be one of three types, a constant, an add, or a multiply. Nothing more, nothing less. So in the switch block, we have three cases. One for constant, one for add, one for multiply. We don't even need a default. In fact, the compiler will check this for us. If we forgot one of these three, we'll actually get a compile time error from the compiler. This is a very beautiful feature where the explicit structure of our hierarchy, an expr is either a constant, an add, or a multiply, is reflected precisely in our switch expressions. Switching over an expr is either a constant, an add, or a multiply. Now for the final feature from Project Amber that we need before we see some examples of data-oriented programming. You'll recall from earlier the record class. The header of the declaration tells you about the contents of the record. In this case, for record class point, we have two components, x and y, both of type int. And remember, the record classes give you accessor methods for free. Imagine we want to test if a value is a point and extract the x and y components if it is. Clearly, we can do this with pattern matching with a type pattern. We can match it against point p, and in the then block, we can use the accessor methods and the pattern variable p to extract the values. But this pattern, is so common, pattern matching with a record type pattern and then extracting the components, that we can actually capture it as a new pattern, a record pattern. The record pattern here is given in the blue box. This particular record pattern looks like the header of the record class declaration. Its semantics is a little more involved. To match this record pattern, we first of all test whether the value is of type point. If it isn't, then pattern matching fails. If it is, then we cast the value to the type point and then use this to extract the component values using the accessor methods, and then we initialize the pattern variables with those values. And then we're free to use those pattern variables in the then block. Remember, data-oriented programming is a new technique for Java programmers where you model real-world data as immutable Java data, and you keep the code that acts on this data separate. And to do this, we have new features from Project Amber to make this more useful. More specifically, we use record classes to model the data. We use sealed interfaces and classes to to model alternatives or choices of data types, and we use pattern matching to process the data. So let's see some examples. First example is an example of a complex return type. In Java 5, we introduced a new type called future. Now, future represents computation that may run concurrently with its initiator. Computation represented by future may have not yet been started, may be started but not completed, may have completed either successfully or with an exception, may have timed out, or it may have been cancelled by an interruption. If we look at the get method for the future class, we see that this reflects all those possibilities. If the computation is not yet finished, the get method will block until one of these completion modes occurs. And if it's successful, it will return the result of the computation. That's the value of type v there. If the computation completed by throwing an exception, this exception would be wrapped in an execution exception. If the computation timed out or was interrupted, a different kind of exception would be thrown. So once I've given you this explanation, you can look at this declaration and you can understand how it works. The API is quite precise, but it's somewhat painful to use because there are multiple control paths. The normal path, where the call to the get method returns a value, that's given in the try block, and numerous failure paths, each of which must be handled in a separate catch block, and I've given the 3 catch blocks there on the side. We get very little help from the compiler to make sure we've done this properly. Let's look again at this problem, but from a data-oriented perspective. What is it that we want to model? Well, let's say that the get method always returns a value, a piece of data. Okay, and what can this value be? Well, it's either something that's going to model success, it's either something modeling failure, something modeling a timeout, or something modeling an interruption. So let's follow this train of thought. Let's say that the get method returns an async return of v. So a value of type async return of v. This is the data that we're going to get out of the get method. Let's think about that data. Well, it can be one of those 4 things we just thought about, right? Let's model success using a record class success, which has one record component containing the return value. Let's model the failure using a record class with a record class called failure with a throwable component. Let's model the timeout using a record class timeout, which has no components. And let's model the possibility of being interrupted using a record class interrupted, again, with no components. These are the only possible data types. So let's seal the async return interface. So that's all it implements, these 4 record types. Now, this is a very beautiful declaration that matches perfectly our design intuition. The 4 possibilities of the value returned by the get method are modeled by the 4 record classes that all implement the sealed interface. Let's look at the client experience of using this version of the return type. And this is where there's a real win. We invoke the get method to get a result. Now we want to examine the result. Well, we're going to use a switch. What are the implementations of async return? Well, first it could be a success. So we use a record pattern to match against this value. Or it could be a failure. So we use another record pattern to match against that possibility. It could be a timeout. Again, we use a record pattern to match that possibility. Finally, it could be an interrupted value. And again, we use a record pattern to match that. And that's it. The 4 possible data types of async return, which are modeled using record classes, could be matched by a switch with 4 clauses, each one using a record pattern to match the record class. So note that we're still dealing with all 4 cases, but with this redesign, we can handle the cases uniformly and more compactly. We have a much simpler control flow, and each case is defined more precisely. We don't have to worry about accessing a value that might not have been initialized, for example. Each case is dealt with by a separate clause in the switch block. And every time we write these switches, the compiler checks that we haven't forgot anything. If we have, it's called a compile time, not runtime. Let's have a quick look at another example. This is the prototypical example of data-oriented programming, JSON. Lots of external world data is JSON. We'd like to represent this internally as a Java value, but remember we're going to follow our data-oriented programming perspective. Let's make a start. Let's call the type of JSON values JSON value. What are the data types of JSON? Well, if you read the spec, there are 6. Let's have a look at how to model them. First, a JSON value could be a JSON string. So let's model this using a record class JSON string with a component of type string. Second, a JSON value could be a number. So let's model that as a record class JSON number that contains a double. Third, a JSON value can be the dreaded null value. So let's model that using a record class JSON null. Note that this record class doesn't have any components. It's used purely to model null values. Fourth, a JSON value could be a Boolean. Again, we model this using a record class JSON Boolean that contains a Boolean component. It's becoming almost automatic, right? Now we get to the exciting data types. Number 5, a JSON value could be a JSON array, which is an ordered list of JSON values. So we're going to model that as a record class JSON array with a component of type Java list of JSON values. Finally, a JSON value could be a JSON object, which is the unordered collection of name-value pairs. And we'll model this with a record class JSON object with a component that contains a Java map from strings to JSON values. And that's it. So let's seal up the interface so we can exclude any other possible implementation of JSON values. And again, just look at the beautiful declaration here. It's declarative, it declares precisely what we want, and moreover, it's a strongly typed model of JSON, right? The numbers are modeled as Java numbers, the Booleans as Java Booleans, strings as Java strings. It's classically beautiful Java code, but we've used these new Project Amber tools to write them in this declarative, precise, and lightweight style, the data-oriented style. Now, as you might have guessed from the previous example, the real win is not this beautiful hierarchy, actually, but the nice client experience. So what do you want to do with JSON values? Well, typically, if you have a JSON value, you'd expect it to be a JSON object, and you want to look for some value associated with a key. So as an example, let's imagine we've got a JSON value. We want to look at the values associated with the keys, name, age, and city, and then we're going to do something with those values. So first thing we do is to make sure that the JSON value is actually a JSON object and not one of the other 5 data types. And we do that using pattern matching. We want to match it against a record pattern JSON object. If pattern matching succeeds, the pattern variable pairs will contain the Java map representing the key value pairs. The next thing to do is extract the value associated with the key name out of the map, which I do using the get method. This value will be a JSON value, but I want to make sure that that JSON value is a JSON string. How do I do that? Again, I use a pattern. But we're not done because I want to extract the value associated with the key age as well. I do this exactly the same way using the get method on the map and then checking that this value is, in this case, the JSON number. And I need to do the same again to get the city value. Now, the cool thing is that in the then block, we can use the pattern variables name, age, and city directly. Just take a moment to look at the code in the box. It's essentially a query that navigates a JSON value. It's an expression, not a statement. There are no statements here. If the query succeeds, then the expression has the value true, and the pattern variables are initialized with the values we want. And those pattern variables, remember, are strongly typed Java variables. If the query fails, the JSON value didn't have those keys, the values weren't of the expected type or whatever, then no problem. By the semantics of pattern matching, the expression just evaluates to false. No exceptions, no try-catch blocks, no nulls, no null pointer exceptions, nothing. Completely declarative. Okay, so I'm nearly out of time. Let's wrap up. Remember, Data-oriented programming is a new technique for Java programmers where you, 1, model real-world data as immutable Java data, and you, 2, keep the code that acts on the data separate. Project Amber is shipping features to make this easy with low cost to the programmer. More specifically, we use record classes to model the data. We use sealed classes and interfaces to model alternatives or choices of data types. And we use pattern matching to process the data. And just to make it clear again, I'm not saying that data-oriented programming should replace object-oriented programming, that it's the end of object-oriented programming. Far from it. Java is an object-oriented language. It's a great object-oriented language. And object-oriented programming is great for many things. All I'm saying is there are cases that are better served with a slightly different discipline. It's not an either-or situation. It's not a multi-language solution. It's a multi-discipline solution, and it's all Java. The new features from Project Amber have been very carefully designed to make it dramatically easier to write, reason about, and maintain programs in this data-oriented style. And with that, thank you very much and enjoy the rest of the conference.